Hello, this is the next video in a playlist that I'm calling Applied Multivariate Analysis. And we're in chapter 4, part of the playlist, which I'm calling the multivariate normal distribution. And let's jump into today's topic, which is conditional distribution of multivariate normal. Now let's suppose we have a multivariate normal that has been partitioned. In the first partition consists of p variables, so it's a p by 1 vector, and x, which is a q by 1 vector. And then the mean vectors in the covariance matrix is similarly partitioned. Now the conditional distribution of y given x, which we'll call f of y given x, that's this notation here, it's multivariate normal with mean and then given by this expression here, the mean partition, the mean of y, the covariance of matrix, y and x, which, is this upper right inverse of xx times x times y. Now notice that this is the equation of a line. So remember in college algebra we had, a plus mx plus, that type of equation for points. So y, this is the slope, and it's actually called the matrix of regression coefficients, which deals with the slope of those lines, x, and then it's centered on the mean of x. So anyway, so let's do a quick example. Let's let the x1, 2, 3, and 4 be distributed multivariate normal, 4 components, mean vector 1, 2, 0, 3, variance covariance matrix as is on the screen. Now we want the distribution of y, or x1, x3, given x2, x4. Now notice it's not perfectly partitioned like the formula where it says all the components of y are at the top and all the components of x are at the bottom. This is kind of separated. So there's two approaches here. One, you can, when you create the mean and the variance using these matrix formulas, you just pick and choose which ones you want. Or you physically move the 3 to the second spot and the 2 to the second spot, which means you have to move the mean vector around and you have to move the covariance matrix around. So that's one approach, and we're going to just try to pick and choose on this for this example. So the mean, which is, let's see if I can see it. Yeah. So it's the mean of y, which is 1 and 0. And then it's sigma yx. So remember, this has to move around. So this is sigma, or this is the covariance between 1 and 2, which is 0. This is the covariance between 1 and 4, which is 3. The covariance of 3 and 1. And this is the covariance of 3 and 4. Right? So anyway, that's how you pick them apart. And x you just leave as x2, x4, because that's what we're conditioning on. And the mean of x is 2 and 3. Yep, -2, -3. And then when you do this matrix multiplication, and I encourage every one of you to do this, you get this equation here on the right. So since we're conditioned on x2 and 3, we have to be given numbers x2 and 3. And then once we're given those numbers, then we know the mean vector of y given x. Now the variance of sigma is the respective covariances matrix. You do this multiplication and you get this equation here. Now we're going to do an R illustration to show you that indeed you do come up with these values. So let me expand it. So remember this, 104, 26, 94, 104, 26, 94. So we're going to use the mass library, and I guess technically we don't have to, so I don't know why I do, but I load it. I'll take that out next time. So n is 1,000. Again, we don't need that, but we do need mu, the mean vector of 1, 2, 0, 3, and that's what we use in the example. And this is the variance covariance matrix that we use in the example. Now, to find the variance covariance matrix of y, we want row 1 and 3, and we want column 1 and 3. And then that produces this matrix. And if you compare that, if you rewind to the previous example, that's exactly what it was. Now this sigma sub yx, that means we want the 1 and 3 rows, but the x were the 2 and the 4. And so this produces this matrix, which is exactly what we used in the example. Now sigma yx is the transpose of sigma xy, so I just transpose it and we get this, which is what we used up in the example. Now sigma xx, we want row 2, column row 2, row 4, column 2, column 4, and that's this matrix here. And now when we do this multiplication, sigma sub yy minus sigma sub yx times the inverse of sigma xx times sigma xy, I'm going to store that in conditional sigma, because I want to, this is why I used mass, because it has this function called fractions. So it will express your results in fractions. And so we look at the result and it's 104, 26, 94. Of course it's divided by 35, and that's what was in the example right here. So we do get the exact results, as we should. So now, if we want to look at the mean vector of y, we want the first and third components of the mean vector, which is 1, 0. The mean of x is the second and the fourth component, which is 2 and 3. Okay. So let's, next section is the sum of two multivariate normal random vectors. So let's say we have a mean vector y, or a random vector y that's distributed as normal, mean, mu, and variance covariance sigma, and we have a random vector x that has the same number of components, so it's p, with some mean and some variance covariance matrices. They're the same size and they're independent, and that's kind of critical here. I think in later sections we may look at where they're not independent, but here they are. So the distribution of y plus x, remember we're adding vectors, so they have to be the same dimensions. It's also a normal random variable, multivariate normal, p dimensions, mean mu sub y plus mu sub x. You just add the means. And the variance covariance matrix, you just add the variance covariance matrix. And to see that, if we calculate the expected value of x or y plus x, expectation's a linear operator, so it goes into both. Well, the mean of y is what we call mu y, and the mean of x is mu x. To look at the covariance of y plus x, remember, co means 2, and this will help you out in the long run. You put 2 copies there. We want the covariance of y plus x and y plus x. So now you distribute this. So you look at the covariance of y and y, the covariance of y and x, the covariance of x and y, the covariance of x and x. Now, the covariance, since y and x are independent, the covariance is 0, and then the covariance of x and y is the same thing, so they're independent. So the covariance of y is sigma yy, it's just the covariance of y, and the covariance of x. So it is correct, at least the mean and the variance. We didn't prove that it's normally distributed, but it is. Now the difference of two mean vectors, or the random vectors, now they have to be the same dimensions, is again multivariate normal with mean mu y minus mu x. And the sigmas are added. And we can look at that. So the expected value of y minus x, expectation goes into both, and we're left with the difference of the mean vectors. Now the covariance of y minus x, remember you make 2 copies, then you take the covariance of y and y, covariance of y and x. Now remember the minus, covariance of y minus x, that's where that minus is, and then minus covariance of x and y, and then plus the covariance of x and x. These are independent, so they're 0, and we're just left with the addition of the covariance matrix. Now, another way to think about these formulas, and they don't provide this in many books, but I think they should, is since y and x are independent, then they're multivariate normal. So you can create a random vector with partitioned, y and x. And then it's multivariate normal with dimensions 2p, or p plus p. And since they're independents, all the off diagonals, or the off block diagonals, are 0. Now, if we create a matrix that's p by 2p, that the first p components is just ones down the diagonal. So it's like the identity matrix. And then the last p columns are the identity matrix again, just ones down the diagonal. And then if you look at a times y minus x, this gets the vector y plus x. Because if you think about it, this row times this vector, it picks off the first component of y and adds it to the first component of x. And isn't that what we're doing here? The first two components are added. Now the second row, it takes the second components from each vector and adds them, the third, the fourth, the fifth, all the way to p. And so this recreates this y plus x. And then we next use a previous section where we looked at the distribution of linear combinations. And this is a linear combination of this random vector. And then if you look at that theory, you get the exact same thing that we were mentioned right there. And to see the minus, it's the same matrix, A matrix, but you put minus ones down this diagonal. So when you take this multiplication, you subtract off the x components, which is what we need. And then again, you just look at a previous section, distribution of linear combinations, and you can get the result. Okay, well, we're at 11 minutes, so I'm going to stop here. Hopefully you enjoyed this. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.